Section 2-4, continuity and discontinuity. The objective of this section is given a function, determine points of continuity and discontinuity, and find one-sided limits. All right, so let's start out with just a simple definition here for what continuity is. We'll define this much better here coming up. But for right now, just to give ourselves a working definition so we can look at some examples and understand what we mean by continuous. If you can do the following, a function that can be sketched from left to right without lifting your pencil will meet our idea here, or our working idea of what a continuous function is. All right, so if you can sketch it from left to right without lifting your pencil, that is a continuous function. All right, so let's take a look at a couple of examples. These are on page 46 there in your book, and there are actually several different sketches there, a total of 6 of them that we're going to look at each one. Some of these will be continuous functions, some of them will be discontinuous functions, and we're going to note why some are discontinuous and why others are continuous. And in particular, we're going to consider what f of c and the limit as x goes to c of f of x are in each case. And remember that f of c is the actual y value of the function versus the limit as x goes to c is the value the function is approaching, which may or may not be the same as we go through these examples. All right, so let's start out with some discontinuous functions here. And we could, I guess, start with either. It doesn't matter whether we start with continuous or discontinuous. But we'll start with discontinuous, see what properties they have, and then use that to help us make a connection here. So let's take a look at this first sketch. Let's take a function that looks something like this, and we're going to have this function have a hole in the graph here. We'll say that this is at point here C, and we'll define this as the limit of our function. We'll call that L. All right, so obviously we know it's discontinuous here. You can see that it has a hole in the graph, so it's discontinuous. But in terms of f of c and the limit as x goes to c, the function does have a limit. That's the value of L, but I can see that f of c does not exist. There's a hole there. So I'm going to write down that f of c does not exist on this function. F of c does not exist. DNE for does not exist. Okay, let's take a look at another function. In fact, I'll draw something very similar here, actually. I have a hole in the graph, but I'm going to define some point up here. And so let's say that this is at this value of x equals c. And it turns out on this function, the limit is approaching this hole in the graph here. The function from both the left and right side are approaching this value here, so we'll call that our limit L. However, the function value is actually up here. We'll name that as f of c. So in this case, the limit exists. It's approaching that value of L. The function exists. It's the value of f of c. But I can see those two are not equal to each other. So I can see that f of c is not equal to the limit there, the limit as x goes to c of f of x, which I guess I called L, so I'll put that at the end there, that that's the L value we're talking about. Okay. Those two functions, by the way, both have what we've defined as a removable discontinuity. Removable discontinuity, hole in the graph. And you can see either case, doesn't matter whether that point is defined above or below it or not. Those are both removable discontinuities. All right, let's take a look at another set of functions here. Again, both of these will be discontinuous functions. This next one here, let's sketch a graph that looks something like this. Okay, we'll say that this is f of x. And let's say that this is that point at C right here. And so now if you consider the limit of this thing, again, in order to determine the limit, I have to consider what's happening both from the left side and the right side. From the left side, I can see I'm approaching this hole in the graph there, which is some value. But on the right side, I'm approaching that filled in circle there. That is the value of my function, and I can see that it's approaching a different value. So in that case, the limit does not exist, but this point right up here does actually equal the value of my function. We'd call that f of c. So I can see that the difficulty that I'm having with this one is not that f of c does not exist, it's just that the limit does not exist. The limit as x goes to c of f of x, which I called was calling L above there. Actually, I should just simply say it does not exist, since we didn't write L into this one. Okay, but f of c does. All right, let's take a look at one last example. Actually, this previous example here with this discontinuity here, when we jump either up or down or step up or down, is what we call a step discontinuity. So let's write that down. We've seen those two terms there, removable discontinuity and step discontinuity, already in previous sections. The last one here that we'll take a look at, again, that has a discontinuity, is a function maybe that looks like this. And so this is what we call a vertical asymptote on our function. I can see that the limit as I approach c from the left side and the right side just keeps, the function keeps getting bigger and bigger. There is no limit. There is no one y value that the function's approaching, so there's no limit. And I can see also that since there's a vertical asymptote there, that the function does not exist. So f of c does not exist, and the limit as x goes to c of f of x does not exist. So in this case, we had problems with both of those. The limit does not exist and the function does not exist. And this last one here, again, you can call this a removable discontinuity. Our book is going to refer to this as an infinite discontinuity. Okay, but it's also known as a vertical asymptote there. So those are the three types of common types of discontinuities that we're going to see in our functions. All right, so I can see that I have problems here with f of c, and the limit as x goes to c of f of x here in each one of these. In some cases, they're different values, and in some cases, one or the other does not exist. All right, so let's take a look at a couple of examples now for continuous functions. So let's draw a couple of sketches here, and of course we could draw lots of different sketches of functions that are continuous here. I'm going to draw this first one here with a function that's kind of got an interesting feature there to it at c. So let's sketch a function that does something like this. This is going to have a sharp point, or it comes to a point, or it comes to a sudden change in the graph, change in direction. So I'm going to make it look something like this. And we're going to make this the point c. Now, as I approach c here, I can see that the function value is actually approaching this value right here. That's f of c. I can also see that the limit of this function as I approach c is approaching that same value there. So that's also L. Those are the same in this case. So in this case, when I consider the limit and the function value, it looks like f of c is equal to the limit as x goes to c of f of x. They were equal to each other in this case, where we have a continuous function. Now that feature that we see in the graph there, where it's got a sudden change in direction, that's what we call a cusp. We'll define that a little bit more clearly here in a second, but that is what we call a cusp on our graph. And the last one here for a continuous function, a lot of functions that we'll work with obviously have some sort of shape that looks something like this. And we'll just call this the point here at c. And again, we can see that this is approaching this value here of f of c. That's our actual function value, but it's also the limit of this function. So that doubles again as both the limit as well as the function value at c. So again, we can see that f of c turns out to be equal to the limit as x goes to c of f of x. So those are the same. And really that kind of gives us the big hint here as to what the property is that we need in order to guarantee that our function is continuous. So let's look at the formal definition now. The formal definition of continuity at a point is this. There's three parts to the definition. This is our formal definition. This is what you're going to have to go back to every time that somebody asks you, or the book asks you, or the test asks you, or whatever the case may be. If they ask you about continuity and ask you to explain why it's continuous or why it's discontinuous, you always got to come back to this definition right here. Don't talk about that you can sketch the graph from left to right without lifting your pencil. That's just a simple definition. Here's the formal definition you need. If continuity at a point, if the following is true, the function f is continuous at x equals c if and only if the following three hold here. The first thing is that f of c exists. You saw in our examples on the previous slides there that that first sketch we did with the removal discontinuity, as well as the last sketch with the infinite discontinuity, f of c did not exist. So we failed that part of it. The second part of the definition is that the limit as x goes to c of f of x exists. And again, you saw some examples on the previous slide there of functions where that was not the case. In particular, it was the step discontinuity, the third graph, and that infinite discontinuity, the fourth graph. Both of those had problems with the limit there. And finally, the third part of this definition is that the limit as x goes to c of f of x is equal to f of c. In other words, the previous two have to be equal to each other. So the function has to exist, the limit has to exist, and they have to equal each other, is basically what this definition says. Those three things have to happen. And again, going back to the second graph that we sketched there, both f of c exist and the limit exist, but they didn't equal each other, and that's part of the definition that failed there. So we were not continuous with that removable discontinuity where it had that point defined up above. All right, so that's our formal definition. There's a additional point that we need to make here, and that is talking about continuity on an interval. So if you're talking about an interval from A to B, and how we define what it means to be continuous on that interval. Function f is continuous on an interval of x values if and only if it is continuous at each value of x in that interval. So in other words, if we want to show continuity on an entire interval or an entire domain, we have to explain why all three parts of that definition of continuity at a point are met for every single point in that interval or every single point in that domain. All right. The other thing to note here is the following. It says that at the endpoints of a closed interval, now when we say a closed interval, we're talking about an interval in which we're including the endpoints. So if you say the interval from 1 to 10 and it's a closed interval from 1 to 10, that means you're including all the points from 1 to 10 as well as the endpoints 1 and 10. Okay? So at the endpoints of a closed interval, only the one-sided limits need to equal the function value. And we'll talk a little bit more about one-sided limits. That was part of our objective here. But if you recall, when we talked about finding limits graphically, you had to consider both what was happening from the left side as well as the right side on that graph in order to determine the limit. So when we talk about one-sided limits, sometimes we want to just focus on what's happening just on the left side or just on the right side, not both. That's a one-sided limit. So what this is saying is at an endpoint here, your function does not exist on one side of that endpoint. It's not part of the domain that you're considering. And so because of that fact, at an endpoint, your limit does not exist because of the fact that on one side of that endpoint, your function isn't there. Your function is not defined. which means you'd always fail this test of continuity at an endpoint because of the fact that you'd lose the limit at the endpoint. What this is saying is you don't have to worry about the limit on the side at which the function does not exist. We can ignore that. Okay? And finally, they give us a definition of a cusp. And a cusp is a point at which the function is continuous, but the derivative is discontinuous. And we'll deal more with that definition. But what we see there is you have a sudden change in direction. You have a sudden change in slope. And so because of that, that's why the derivative is not going to exist there. It's not going to be continuous, actually. All right, with that, let's take a look at one-sided limits. We mentioned it just a second ago, but let's take a look at it a little bit closer here. There are two one-sided limits here, of course, that we want to consider. There's both a left side and a right side. And you'll notice the notation that we use here to indicate a left-sided limit and a right-sided limit is that little plus or minus that we put as a superscript next to the c. So we write the limit as x goes to c, and then we put a little superscript of a minus sign to indicate the left side of f of x, versus for the right-sided limits, the limit as x goes to c, and we put a little plus for from the right side of c. Now the reason why we use that notation, by the way, if you're wondering where that comes from here exactly, if you were to draw your number line here, and we'll put 0 right here in the middle of that number line. Of course, on the left side of 0, over here on the left side, that's where you're going to find all your negative numbers. And over on the right side of 0, that's of course where we're going to find all of our positive numbers. Thus the notation. The left side of 0 is associated with negative numbers. The right side is positive numbers. So we'll use that plus or minus to indicate left or right. Here is the limit property, and you've actually used this property already. We just didn't formalize it here for you until now because we haven't defined exactly how a one-sided limit is noted. But now that we have that, if we know the notation for it, we can write down this property. It says L is equal to the limit as x goes to c of f of x, if and only if the following is true. So L is the limit as long as the following is true. That L has to be the limit as x goes to c from the left side of f of x, and L is also the limit as x goes to c from the right side of f of x. I said that you've already used this property because graphically, the way that you find the limit of a function is you actually trace to see what's happening from the left side as well as the right side as you approach this value of c. And as long as you are approaching the same value from both directions, that was your limit. That's all this is saying here. The limit from the left side right here and the limit from the right side right here, those have to be the same. They both have to be equal to L in order for L to be the limit of my function. So again, that's basically what we learned doing this graphically already. All right. Let's take a look at an example here on page 48. This is example 1. And it says, for the piecewise function f shown in figure 2.4k, part A says to plot the function f on your grapher. So let's first of all write down what the function is. They have defined for you what we call a piecewise function. That's because it's actually made up of several equations, but they are each defined on their own domain, or own section of the domain here to make up this function that's made up of pieces, so a piecewise function. So the first part there is x plus 4, and that's defined on the domain if x is less than or equal to 2. And then we have the opposite of x squared plus 8x minus 8, and that's defined if x is between 2 and 5. And the last part of this is x plus 2, and that's if x is greater than or equal to 5. So there's our piecewise function that they've given to us. And again, part A says to plot the function on your grapher. So I'm going to go ahead and do that. They did give you a picture of it there, but I'm going to plug it into our calculator so you see how to actually punch that in and graph this thing. All right, so the first thing we need to do is go to your y equals menu, and we're going to put in the 3 parts here, and this has to be defined in 3 different y equals equations here for us. And basically what we do is we take the function and divide it by its domain. So I'm going to put in parentheses here, the function is x plus 4, the first piece, I should say, of this function. And we're going to divide it by the domain. And the domain of that first one was x is less than or equal to 2. So x, now to find less than or equal to, you press second and then your math button, second test. Less than or equal is all the way down there to the bottom, number 6. X less than or equal to 2. Take the function and divide it by its domain. And we'll do that same thing for the next piece here. It's in negative x squared plus 8x minus 8. And we'll divide that by its domain. That was from 2 to 5. So 2 less than x. Now your calculator does not understand a double inequality like we have defined there in the book. So we have to go back to what that actually means. It means 2 is less than x and, which and you'll find under your test menu again, but go over to logic, there's and x is less than 5. Okay, but you can't put in a double inequality there. But you got to use and combine those 2 single inequalities to make that same thing as the double. All right, and then finally the last piece there is x plus 2. Oops. And we divide that by the domain of x greater than or equal to 5. And those are the 3 pieces that make up our function. They gave us a window here, I guess, in the book there, so I'm going to just use the same window that they've shown. But obviously you could start out with this in the standard window and sketch it from there. The fact that you know that the key values here where it changes in these pieces, there's at 2 and 5, would perhaps help you focus in on this. But I'm just going to go from 0 to 8 like they showed, a scale of 1, and we'll go 0 to 10 just like they showed there for the y's. And here comes a sketch of our function. Pretty decent sketch. Sometimes it might show a gap in the function that's not actually supposed to be there, and other times it might not show one that's supposed to be. So you got to be a little bit cautious here. For example, at x equals 2, it looks like there's a step discontinuity there, but again, sometimes your calculator can have some difficulty. And even over there at x equals 5, it looks like those 2 are continuous. Looks like those 2 pieces come together there, but you got to be careful. Your calculator could be trying to sketch that the best it can, but it might be off a little bit. And that's really what part B and C are going to get into here. Part B says, does f of x have a limit as x approaches 2? So for part B, again, we're not going to do this just by looking at the graph. We're going to go through and actually find the limit here. But to do so, the question is about the limit as x approaching 2. We're going to actually find the one-sided limits and then use that property to help us figure out if the limit exists or not. So let's find the limit as x goes to 2 from the left side. And from the left side of 2, that would be the domain where x is less than or equal to 2 there. So that's the x plus 4. And we're going to use our substitution method that we know. Just plug in x is 2, 2 plus 4 is 6. So the limit as x goes to 2 from the left side is approaching 6. And now take the limit as x goes to 2 from the right side. Now from the right side, the function is, that's the domain that's x greater than 2 there. So that's the middle section here. It's the negative x squared plus 8x minus 8. And as x goes to 2, you'll have a negative 2 squared. That's a negative 4. Plus 8 times 2, that's 16. So negative 4 plus 16 is positive 12. Minus 8 gives us 4. So based on that work there, the fact that the limit from the left side is 6, but the limit from the right side is 4, and coupled with the property that we just talked about in the last section, or on the last slide, that tells me that the limit as x goes to 2 must not exist. Limit as x goes to 2 of f of x does not exist. All right, that's the first part of the question. The second part says, explain, which we have explained that already because the one-sided limits are different. But it also asks, is f continuous at x equals 2? So let's go through the definition of continuity. And really these are a series of questions that we need to answer here for ourselves. So the first question we need to answer is, does f of c exist? In this case, we're talking about c being 2. So does f of 2 exist? And according to the definition, if I go back up here to our function, it says that when x is less than or equal to 2, we use the first piece of this function. That would be the x plus 4. So I can calculate that f of 2 is equal to 4. The 2 plus 4 gives us 6. So yes, in fact, f of 2 does exist. In fact, maybe I'll put a yes at the end of this here to answer our question. We'll say yes to the first part. The second question is, does the limit exist? Does the limit as x goes to 2 of f of x exist? And actually, we already did the work for that up above. We found that the limit as x goes to 2 of f of x does not exist. There is a big no then. And if you're trying to show that something is continuous or discontinuous, as soon as you find one of these things that's not true, or that the answer here is no, you can stop. You've found that this thing is discontinuous. So we can write a concluding statement here and say, thus, f of x is discontinuous at x equals 2. Okay. You can check the third part of this definition if you wanted to, but I don't need to. As soon as I find one that's one of these that's not true, we can stop. All right, now part C on this one is going to ask us to do pretty much the same thing. The only difference is they're going to ask about the limit as x goes to 5. So we're looking at the key value of 5 there. So again, to evaluate this thing, I'm going to focus on what's happening as I approach 5 from both the left side and the right side. So as I approach 5 from the left side, let me go back up here to our definition. That's for x is less than 5. So as x approaches 5 from the left side, that's the middle piece of this function. So that's the negative x squared plus 8x minus 8. Negative x squared plus 8x minus 8. And let's go ahead and evaluate that. If we plug in 5, the opposite of 5 squared would be a negative 25. Plus 8 times 5, that's 40. So negative 25 plus 40 is positive 15. Minus 8 is 7. And now do the same thing from the other side. The limit as x goes to 5 from the right side. And again, if you go back to your definition here of your function, the piece that we want is for x is greater than 5. And so that would be the last piece of this function. That's the x plus 2 piece. X plus 2. So again, using their substitution method there, 5 plus 2 gives me 7. Now I have the limit from the left side is equal to the limit from the right side, and so based on the property again that we've just talked about, that means that the limit as x goes to 5 of f of x is equal to 7. It not only exists, but it's equal to this value of 7. Okay, and that's our explanation there as to why it exists and why it's equal to 7. Part C also asks, is f continuous at x equals 5? So now we're going to go back to this definition of continuity. And again, it's a series of questions really that we've got to answer here for ourselves. So the first one is, does f of 5 exist? And so I can take 5 and I can plug it into my function. If I go back up to the definition here, the definition says in the very last piece, if x is greater than or equal to 5, then the function we evaluate is x plus 5. So f of 5 is equal to x plus 5, so that'd be 5 plus, excuse me, x plus 2. That would be 5 plus 2, that's 7. So does f of 5 exist? That's a big yes. I get some number out when I plug in 5. The second part of our definition of continuity is, does the limit as x approaches, oops, not 1, but we're approaching 5 here, as x approaches 5 exist? And actually, we've already done the work up above there, and we found that the limit as x approaches 5 of f of x was equal to 7. So that's another yes, the limit exists. And you can see that we're going to meet the last piece of this definition based on our previous two parts here. 3 says, does f of 5 equal the limit as x goes to 5 of f of x? And you can see from our work up above there, they're both equal to 7. So f of 5 we know is equal to 7, which is equal to the limit as x goes to 5 of f of x. So this is a big yes as well. So because we've met all 3 parts of this, I'm only continuous if I meet all 3 of these. And so I can conclude that the function is continuous at x equals 5. Thus, f of x is continuous at x equals 5. Okay, so our calculator did a pretty good job there of showing what this function looks like, with the fact that it did show a discontinuity at 2, but yet it showed a continuity at 5. But again, I'm not using the calculator graph or any graph to verify why this is. I'm going back to the definition of continuity to verify why we're continuous or why we are not continuous. All right, and that is the end of the first part here of this section.